Welcome everybody to Lecture 4, Databases and Information Systems in the winter semester 23-24. As I was saying, we are having technical problems on all kinds of fronts, but yeah, I hope we will handle. So overview over today's lecture, I will say something about this is already the first mistake here. The third exercise sheet was, I think, database design. Yeah, but that's completely in line with the happenings of the last hour. And the contents is today about more database stuff. And we will talk about it as we go along. So right now the exercise sheet is not yet uploaded on Daphne because there are connection problems, microphone problems, all kinds of problems. But we just tango on. Experience with exercise sheet 3. This is also wrong. So a very nice lecture, easy sheet. Data collection was a bit tedious. Some of you said, many of you already attended the old course. So in the feedback you said, yeah, I watched this, but it was still very interesting. Here are some quotes. Lecture was a really great introduction to databases. Databases used to scare me, but the way you teach this is actually fun. I also think database is a really super interesting topic. Very good sheet, was fun to think about the design. Feel like I'm learning a lot by doing each of the exercises. This is for all of you who are not doing the exercises, do them. Really easy, but also good to get into SQLite 3. So that was the simple, easy to use database system we used. Normally database systems are not easy to use. Several of you said that, a little tedious to gather the information. I can't show you the exercise sheet again at the moment. But the first exercise was to gather the data yourself, just to clarify again why we did it like that. By the way, is the sound too loud? Is it louder than usual? It's not too loud. It's just too loud for my ears. Okay, please complain if we should turn it down. I think it's a little louder than usual, but fine with me. So the reason we didn't give you the information already was because you had to come up with a schema yourself, how to put it into tables. And if we would have given you the information, we would have already solved part of the task. And if some of you found that a little tedious, well, that's, I think, part of this work. So in our group, we work a lot with data and just doing something with the data, also these tedious tasks, is always part of the work, and sometimes a big part of the work. I actually like it. It's very meditative. Some of you didn't seem to like it. And I think it wasn't a lot of work here. It was data about 4 movies. I wrote R scripts and used Excel to tidy the data. I was surprised by that comment. But that's maybe the typical computer science attitude. You could do it manually in 5 minutes, but why not write complicated scripts to do it automatically in 3 hours? But it's more fun. Okay, you certainly didn't need R scripts in Excel for data about 4 movies. Sad to see how sexist the film industry is. I also realized by looking at all the data in preparation of this sheet, you see a lot, it's clearly male dominated. Which it shouldn't be. I mean, it's film. It's a bit louder, but not too loud. Yeah, somebody wrote that, but we turned it down now. No, that comment was, somebody used over 50% females to counterbalance this. So we started late, but that was a short organizational part, so we are back in time again. So we have a lot of slides today, but I think many of them are very easy and quick to go through. So it's again a completely new lecture, so you see all these small little mistakes. That's typical. It's an extreme amount of work to prepare a completely new lecture from nothing. So this is not from a textbook or not from previous stuff we have done. It's completely new, but yeah, let's see how it goes. So the first part is a bit of a recap of the last part of the last lecture, but in a new way. So in case, let's just see. So in lecture 3, we have learned, like by example, lecture 3 was mainly about database design. You have data, how do you put it into tables? It's surprisingly non-trivial, But we also learned a little bit of SQL, otherwise it's no fun if you cannot ask your query your data. And we had these queries of the form select from where. That's how the typical SQL query looks like, and we kind of learned it by example. And we just learned how to, it was part of the sheet to also run some queries, find some queries, but we didn't really bother how a system actually executes such queries. And how it executes the queries, so that's today's topic. Internally, so what does the database engine do if you give it such a query? We will see lots of examples in the following. It implements operations, so like, and what operations are, we will see them in the following. And then it translates the SQL query to a sequence of operations. And then this is called query planning, which is also part of the title of this lecture, and then it executes the sequence of operations. So that's very high level. You will see now what this means. And so we start again with 3 operations, which we kind of already saw in the last lecture, but we didn't. Now we have some new names: projection, selection, Cartesian product. We call this, maybe I quickly write this down. We called this cross product in the last lecture. But it's the same. Cross product, it's absolutely the same, but in the database world, you typically call it Cartesian product, and we already established that Cartesian comes from René Descartes. So, and these operations, we kind of already introduced them informally in the last lecture, and today, so this will be a bit of a repetition, but now we will define them mathematically. Now each operation takes some input. The output is always a single table. And before we provide the definition, let's first repeat this slide from the last lecture. It's our formal definition of a table. And a table, so a table, you will see many examples again in the lecture, but you know what a table is: column, rows. So you have a sequence of column names, we always call that C. You have a sequence of domain names, so the values in every column come from some domain, can be the strings, the integers, the real numbers. And then our rows are a multi-set of tuples. Multi-sets because the exact same row can occur multiple times. So it's a set. The order doesn't mean anything. There is no order, but you can have the same item multiple times. And we talked about multisets in the last lecture. This should be 3 here and not 4. As I said, I think we will have a lot of these small little mistakes. And we also call it tuple. When we say tuple here, that's the mathematical way. If you have something with k components, tuple or row, I will use them synonymously. But then you understand why it's called R. Tuples are because the tuples are the rows. Okay. And here's some basic notation. We'll just make our work simpler in the following. The animation was missing on that slide, but I think that doesn't matter. So if I have 2 tuples, for example, the column names, or even 2 rows, if I just write them side by side like this, this isn't supposed to mean some nested thing, but it's just the concatenation of the 2. There's not really a standard notation for concatenating 2 tuples. We will just write it like this. And then we will also write, if I have a row or a tuple like this, and I call it R, then I just use the programming notation with square brackets if I want to denote a value in a particular column. So we will have that several times. And we will see Boolean values quite a bit in the following. We could just write true and false, but true and false are not really, these are strings, not really mathematical values. In mathematics, you have these funny symbols here to denote true and false, so you will see those a bit in the following. Now the microphone, this is also having problems, so this is true and false. Okay, and now we start with the, I just shouldn't move. I don't move. Projection is the first operation, and it's really simple. And for each of the slides, I will give you the formal definition and then an example. So if you realize what's causing these noises in the microphone, just tell me. You see me, maybe it's subtle movements, or I don't know what's happening. So what project does is it takes a table, it takes a sequence of columns and an additional boolean, which can be either true or false. And if you leave this out, somehow we leave it out, then it's just false. And what does it do? It produces a table. So this is essentially select some columns from a table. So I have let's maybe try to understand it maybe let's first go to the example. And here's an example, and then I go, maybe that's the way to explain it. First understand it by the example, and you have seen this in the last lecture already, it's just more formal. Here I have a table, and I always do it like this. In this lecture I have the signature of the schema of the table by just writing down how I created this. So this is about people. I have an ID, a first and a last name. Here we see two people with the same first and last name. And now I have this Sparkle SQL query, select distinct. I just pick two columns here. So I have a list of columns. Here it's column names, first and last. And in the operation takes as argument a table. So that's this table. Column indices, starting from 1. Maybe I should write that on the slide. So first, last is 2, 3. And note, that's a subtle thing, this is a sequence of column indices. I could also have the same column indexed twice, so I could even duplicate columns if I wanted to. I could also here write first, first, last, last, and then I would write here 2, 2, 3, 3. And then distinct or not, here it's true. And distinct means if I would just just take these two columns and remove Anne Hathaway is there twice, so the exact same row is there twice. In the original table, it was not the same row because the ID was different. But if I just take these two rows, it's there twice. And by using the distinct, this row is then there only once. So that's so we have this simple SQL query, and that's the operation it translates to. And now let's go back to the formal definition here. And I just put this formal definition so that it's absolutely clear. An example is always good to understand how it works in principle. A definition tells you how it works in detail. So arbitrary sequence of column indices, and then I just pick those columns with those indices. That's why I have the double indices here. And then I just pick the corresponding values from the columns. And if distinct is true, I remove all duplicates. Is there any question? You should ask it now. Any question about the notation or about what this operation does? Because we will now see several operations like this. Yeah? Okay, I should do something with the... So? Mm-hmm. Why does it say select from T and not from people on slide 9? It's a good question. The only reason is I just took T as a shortcut for people here. I could have also written people here. It's a good question, but it doesn't really mean anything. It's just so that this looks more compact. Because in the following I will often have variable names here. Otherwise it's project people, and then it's kind of hard to see that people is a table and project is an... And yes, here it says, oh yeah, you're right, it should be ID int, it should be text int. Okay, now I have a problem because now it will be, the line will be too long. Okay, now I have to show my amazing PowerPoint skills. Let's see. So now it should be, oh yeah, you're right. My PowerPoint skills may be amazing, my other skills not. It should be like this, yeah. So you're completely right. Thank you for paying attention. So it's all text here because I took Wikidata IDs for IDs. Any other question about this slide before we move on, or about this definition? Okay, let's move on. So this is selecting columns. Now the next operation is selecting rows. And let's first look at an example and then at the formal definition. So here it's the same problem. Okay. We will correct these small problems while we are, because it's the same table, so we have the same problem here. So now I'm selecting some, the operation is now given a table, and now you have a predicate here. So it's an, I think I wrote this differently in the following. Maybe let's go back to the formal definition first in this case. I think it's better. So my input is a table, columns, domains, rows, and I have a function now. So the function takes, this here is just give me a row, so something from the domain for row 1 and so on. And then for each row, tell me, for each potential row, tell me true or false. So this is also called a predicate. And then I just return all the rows where this predicate evaluates to true. So this is the select function. So it looks more complicated than it is. It doesn't do anything with the columns, the same domains, it just changes the row. So it selects certain rows. And note the confusion here. This operation is called select, but when you say something about the rows, and it appears in the where clause of the select of the SQL query. So you see it here. Let's see this example here. So here I'm saying select from this table the rows where the first name is Anne. So this is in the where clause, not in the select clause, but the operation is called select. And that's just how it is. That's historically so. So these operations, they are very old. They come from this 1969 papers, and they just have their names. And SQL is a bit younger. And I want to, this here is written in a bit strange way, and I want to write it a bit differently. I think in the following I often write it like this. The second argument here is a function. And now how do I write an anonymous function in, okay, I think I need to steal, this is how I write it here. Let me do some, yeah. This is how I write an anonymous function in the following many times. Yeah. So this is just a function which just, for a given row checks whether the second column is Anne, and then it's true, and otherwise it's false. So it's quite simple, really. It's just introducing the formalism. Okay, let's go on. The Cartesian product. So it's a bit longer than cross product. So you get two tables now, like this. And then the result is a table T. And this is what we have seen on the slide further some slides ago. This is just concatenating the two column names and corresponding domain names. And this is now the cross product. And we have defined this in the last lecture. So it's all concatenations of tuples, rows from the two tables, and it's just all combination. Any row from the first table with any row from the second table. So this is the mathematical correct way to write the product. And note, this is we have seen this in the last lecture. If you do this, if you form the cross product or Cartesian product of two tables, the size of the column names add up, but the number of rows multiply. So you get these huge tables. And let's look at a table here. So different examples. So I have here some arbitrary categorization of the human race into three genders, politically correct, female, male, and other. We have these three in Germany. These are the correct Wikidata IDs. And then we also divide the world into stupid and wise people, and now you get all combinations. So this is a statement about humankind. So however you divide the world, you always have stupid and wise people in all camps. It's not the privilege of any one camp. So here we have, and this is also wrong. Oh my, there are a lot of small mistakes here. You can see the development process of these slides. You get the final product, but actually 500 versions before this. So what do we get? So this is actually an example where our combinations make sense. You just get, let's take this row here, and you get all combination of this row with this row. And you see here the number of columns in this table is just 2 plus 2, so 4, and the number of rows is 3 times 2, so 6. You get the combination of every row from this table with every row from that table. And you just write this operation as Cartesian product T1, T2. So we have already seen this in the last lecture. It's nothing really new, but you should just, we write these things as operations now. And one thing which you have seen on the slide, but I haven't mentioned, but let me go back and mention it now. There are also these symbols for, so traditionally, so this is called project, and you often write it like this. So in the literature, you will sometimes see this capital Greek letter pi. Let me maybe also write this here. So this is the capital Greek pi. That's how you also write project. It's just the same thing as a symbol, so it's nothing different. And projection, you always see it as, often see it as sigma. Let me just write sigma here. So that's the small sigma. It's also a Greek letter, but it's just a different way of writing it, but we will often write it like this or like this today. You have a question? Yes?
Why are the inputs of this function d1 till dk and not r1 to rf?
Okay, that's a good question, and that's one reason why I'm putting these formal definitions. This is a function which takes an arbitrary row as input. And how do I explain it? So R is a subset of D1, dk. So yeah, it's a. Let me first ask this question: is this? Do you agree with this? Okay, you agree with this, right? This here is the set of all possible tuples, and this is the set of tuples which we actually have in our table. And you are right. I think why did I do it like this? Because the function you typically give, I think that's the only reason I did it, and I have to think about it whether both are right or whether this is better. The function you put in is typically agnostic of what's in the table, right? You just give a function which you could evaluate on any row if it's a valid row of this domain. So that's why I put it like this. The function you put in, otherwise this function, if I put R here, this function would depend on the table, and I didn't want that. That's the reason why I wrote it like this. Yes, please?
Can you not specify an empty column in a row, so you have null for some value?
Yes.
So then you would need null in every domain, or yeah.
Yes, you are completely right. We didn't talk about null values yet, but yeah, why not? They're in our domain. I mean, we leave the domain open. So we will see code in a second. So when it's again a matter of, so here we have some commands. This will be for the tables we see later here. Yeah. So this is the domain of strings, and now it's again a matter of definition. Are we saying, let me maybe go back to the slide with the formal definition of the table. Yeah, I would just say that these domains include the null value, and then we are fine, right? Because we are not doing anything special with the null value right now. So saying that there is nothing in the table, do you agree? I mean, we could just do that, right? We didn't really, they don't have a special treatment currently, so that's fine. Okay, so we had the short names, we have the, so we have seen these three basic operations. We got used to this formalism a bit. That was the purpose of this so far. And now we talk about what we actually want to talk about. So we have a SQL query and how we execute it on our machine. So now I claim, and we kind of already did that in the last lecture, but very informally and just intuitively, any query of this kind, select comma separated list of column names from some tables where some expression, you can translate it to a sequence of operations, which the database engine then executes. And right now you may think, yeah, well, that's all trivial. I kind of write the things. I mean, this is what you might think here, right? Here I'm just writing select star from tables and it translates to this operation. What's the point, you might think? It's just writing the same thing differently. But you will see now what the point is. There's an important difference. And let's take one example query. And I always do it as follows. So I have different examples, not necessarily always the same tables and so on. I put these, how I created the tables first, so that we can also spot mistakes, so that it's also clear, okay, this is a table with, okay, I didn't put the domains here. I omitted the domains I did that on purpose because I omitted the domains for space reasons only. Should write that here, the domains, to save space. The purpose is really that you see how many columns to save space. And now, what's the sequence of operations here? And now you already see that's not trivial. Now pay attention. So I have this SQL query, which is already a little bit more complicated. You have a question?
I think it should be where rows person ID equals person's ID equals person ID.
Yes, you're completely right. Thank you for paying attention. And I will just solve it by abbreviating this here, right? Then it's also right, is it? Let's quickly check whether it's right now. So I just call it ID here in movies and persons, and here I have to call it by a different name because otherwise I would have the same. Is it correct now? Roles, person ID, persons ID, roles, movie ID, movies ID. Yeah, okay. So now, how do I translate that to a sequence of operations? And here's how I could do it. I could first, okay, I have the Cartesian product between three things. I don't have an operation for, let's say our database has just implementations for these three operations which I have just seen. So let's take first the Cartesian product between movies and persons. This gives me a table T1. Now I take the Cartesian product of that with roles. Now I have a table T2. T2 is now the Cartesian product of all three. So I could have also done this in another order. Note this. Now from T2, I have to select some rows. So this table now, we don't have a picture now. This is now movies, persons, roles. So like they are written above here. First I have these 4 columns, then these 3 columns, then these 2 columns. And let's hope that this is correct. So now I want this ID to be equal to this ID. So that's 1, 2, 3, 4. Maybe let's write it here. So if I concatenate them, I don't want to show these big tables all the time, then it's like this, 5, 6, 7, 8, 9, 10. So now it's 1 should be equal to, no, this is not correct. I did birth date is 2 is not the same thing. It's just one thing. I think it was correct. Birth date is 1, 7, 8, 9. Okay. Yeah, if I have the cross product, they all get concatenated. I concatenate in the order of movie, persons, roles. So these are of my T2 table. These are maybe I should write these. So these are the column indices of my table T2. And now I want this ID to be this ID, movie ID, right? This is R1, it's written here. This is first equal to the 8th, and then 5th equal to the 9th. And then in the end, I want just title and person's name, and that's project. Project gets column indices, and I think we have, I deliberately left this out here. There's a third argument for distinctness, and note, third argument is, writing down here is false by default. And you see, that's already not so easy, right? Translating this SQL query into this sequence of operations. And that's what a query engine has to do. And that's also what you have to do for the exercise sheet, but you have to do that manually. So this is something it's maybe the most important things you should learn for this exercise, for this lecture and exercise sheet. Take a SQL query and translate it to a sequence of operation. And this is exactly what a database engine does. And look, this is something now we can easily execute, right? This is what I said on an earlier slide, maybe was not clear then. For each of these, I could have a function. This is also what you should do for the exercise sheet. I can't show it to you yet because Daphne is down. You will just implement all three. Actually, instead of this one, you will implement another one. And then you can these are just functions which you can call. It's a function which takes two tables, computes another table. This is a function which takes a table and a predicate produces another table. This is just, you could write this almost in code. And this is also how your code will look like. So what you will do for the exercise sheet, you will see a SQL query, you will write down the sequence of operations in code, and then you can execute it. And here's one more important thing. So this was one sequence, but it was not the only sequence. Okay, before we continue, before I say that, two other things. So there are other ways this could have been written. This is as a sequence of operations. I think it's the easiest to understand how you would write it in code. You could write the exact same thing as a nested expression. This is the exact same thing like in one line, right? So inside here I have Cartesian product of movies persons. I take that as the argument of Cartesian product roles. If I go back one slide, it's just plugging T1 into here, then I get this larger expression, then plugging this T2 into here, and then plugging this into here, and then I get a nested expression, right? And this looks scary maybe, so this is really, this SQL query has a mathematical expression. But think about it, this is not any more difficult than how mathematical expressions work, right? If you know how maths work, so this is some basic arithmetic here, you are not scared by such an expression, you will just evaluate it. You will see, okay, let me start here, 3 plus 4, 7 times 4, 28, minus 3, 25, and so on, 57. And guess what the result is. And there's one other way this is typically shown, and that's as a tree. You can also do the same for mathematical expressions, by the way. This is also sometimes very useful. So this same query, so here we have the Cartesian product of two tables, movies and person. This gives me something. The result from that becomes one argument of this. The other argument is this. And here I've just written the additional arguments at the bottom. So this is, you get an expression tree. You could do the same thing for a mathematical expression. And maybe let's do that, just so that it's absolutely clear. So if I have an expression like 3 plus 4 times 7, I could also write this as a tree, right? And this is often done. So now I have the multiplication here of 7. Yeah, so I have 3, 4. Here I have an operator, and also in this tree you could also see how you could evaluate this. So at every node here you could do the plus, you get 7, and then 7 times 7, 49. Any questions about this part? So this was setting the scene for what comes next. Can it happen that the intermediate results are used in multiple places? That's a good question. So then this would not be a tree anymore, right? In principle, you could have it like this, but actually, how it's typically done is trees. So what you would do, so what we do in our engine, we would just compute the result again, but we have a caching mechanism, so we just see, oh, this has already been computed, I don't compute it again. But you're right, in principle. Let me maybe quickly show you this, that this is not just theory, but how it's actually done. So you remember this from the first lecture. This is now Sparkle. We will do that in 2 lectures. So dialect of SQL, but it's the same thing. I execute a query here, and here I get a query execution tree. So this is a tree with all kinds of operations. So this is how database engines always work. I'm surprised how big the tree is. I was expecting a smaller one. Maybe, no, these are all relatively. Do I have a simple query? Yeah, I can do that. Queries quickly become this is maybe a little bit simpler query here. So also you see here it's a tree. Here the operations have different names, but this is an operation. It's also operating on tables. It's the same here. And then you do something with that, you get another table. This table gets input to here. So it's like operations which take tables as input, produce other tables, and so on. And up here you have the result. This is how all database engines work. Any questions about this before we move on? Okay. Now what I wanted to say earlier. So it's very typical that you have more than one sequences, and actually it's typical that you have very, very many sequences of operations. How you do it. And we'll see that in the following. The results are the same for each sequence, but the processing time may be vastly different. And let's just look at a few examples. So here's a very simple query where I just have a cross product of 3 tables. And obviously I could do this in 2 ways. I could first, okay, here I have cast again, not roles, but yeah, let's maybe also fix this for consistency. Let me just write roles here. I have 3 tables, and now since I only have a binary Cartesian product, I have to make up my mind in which order I do it. So I could do it like this: first cross product of movies and persons, then with roles, or first movies and roles and then with persons, and there are more possibilities. Okay, and now the not so easy question: which one should the database engine choose? What do you say? Now, I deliberately wrote this. You have to make some assumptions on the data, so assuming this is real data, and real data means you know something about the sizes and the nature of the tables. Well, what do you think? You are the database engine now. You have to decide, we go with this plan or this plan, this program or this program. Yes?
Like, not all movies will have the older roles, so I think the first one is better.
You say the first one is better? I didn't quite understand the reason you gave.
Not all movies will have the older roles, like all the possible roles. So
Yes, you are saying not all movies have all the possible rows, but this is the cross product. So this will compute all combinations either way.
yes, right.
It will compute, the end result will be the same, and the end result will be huge. It will be the number of rows of this times the number of rows times this. Yes?
Yeah, I think basically you should first
Which one is better?
Sequence 2, because of the matching key, personal key, the two tables.
Okay, interesting. But you said something similar. You said something of matching ID. This is Cartesian product. You're not matching anything. You're taking all combinations. Yes? Okay, both sequences should be the same. Interesting. So already with this simple example, we get different answers, and actually it's not so trivial, which is the point of the second part. Let's keep tuned for the answer, and let's show two other examples. Depends on the data. Somebody writes in the chat, yes. I would take the biggest table at the end. That's good thinking. I agree with that, but we will come back to that. Yes, so there is a difference. It's a small difference because the end result is the same. But it's interesting that already for this simple query, it's not so obvious. Here's another example. So this is, and look at this. Now I have two tables. I take a cross product here, but I do nothing with the rows table. And no, I do something. Yeah, I do something with So which one is, yeah, it's a strange query, but people write strange queries. I mean, people also write strange programs. So I take the cross product of the two tables, movies and roles, and then I select all rows where the score is greater or equal to 8.0. I can do that. And now here are two ways to do this. First, compute the Cartesian product. Oh, again, another mistake here. Lots of small mistakes because I made, yeah, but this doesn't really. So, which way should I do it? First the Cartesian product, then select the rows, or first filter the rows and then do the Cartesian product? Yes?
First filter in the movie database to trim that down and then do the Cartesian product. So
Yeah. Yeah, first filter the rows, then Cartesian product is very expensive, so it's all rows here times all rows here. So if you have anything that makes it smaller, the table, better do that first, right? So the end result will be the same, that's important, but this here will make T1 is now significantly smaller than movies because it only contains the movies with a high score. And so now this Cartesian product will be T2 will be much cheaper than T1. And here's another one, which is also strange. So now I take again the cross product of two tables. I ignore the second table. I have a distinct here, distinct title. And here's one table. It's kind of the obvious way how to do it. It says from two tables. So I take the cross Cartesian product. Then I select the rows. It's kind of the literal translation of this query, right? Just start with the from. It's how we did it in the last lecture. Select rows, select columns. And because it's distinct here, we have a true here. Can you think of another sequence? Now you want to be a good database engine. You want to produce the correct result. Can you think of, and now we haven't defined efficiency yet really, but can you do it more efficiently? Think about what the end product of this query is. Yes?
Can we throw out the Cartesian product completely? Because
Can we throw out the Cartesian product?
Because title comes from movie
Yeah.
and score is also from movie, so in the result the rows table is not related.
Yeah, can we throw out the Cartesian product? I mean, we have a Cartesian product here with roles, but we don't need it. We have no reference to roles here, no reference to roles here. And yes, I mean, you can just do that. We just take, I mean, what is the end result of this? The end result, this will be the distinct title from movies from popular movies with score greater or equal to 8.0. We could just do that right away, right? Just take the movies table with score greater or equal 8.0 and then take the second column from that, the title. And also do distinct here because we might have the same title twice. So now you see it's getting interesting, right? These super simple operations, translating it, and now this is already totally different. I'm even dropping an operation here. It's the same result. And now imagine you are the database system and you have to figure out that this is actually the same, that I can do this. That's not so easy. And here I think it's clear which one is better, right? This one is kind of trivial. I just take movies, filter, just look at those with a high score and take the second column. And here I have this Cartesian product and I have to do the same thing on the huge table. Okay, so that's query planning. Query planning is you are the database engine, you have your SQL query, you have the operations which you have actually implemented, and now you have to translate from this SQL to there to what you actually execute. And now you have to figure out, that was on one of the very first slides, which of these sequences do I take? And this part of this problem is to first realize which sequences there are, right? There are actually very many sequences. Sebastian, does the exercise sheet work? Or not yet? Not yet, okay. Daphne problems are, so some of the problems are, maybe let me just, so the exercise sheet will be, no, we will come back to it later, maybe we see it then. Only do select and project, yeah, same suggestion. So, the obvious question now is, you have many sequences, which one is the best? And every database engine in the world has to deal with that. And here's the basic idea. You have all these operations here. Let's look at this. This is an operation. This is something which the database engine actually has to execute, has to call, has a function for this, and this is where the time goes. So what I can do, what's written on the next slide is estimate the cost of this. How long is this going to take? How long is this going to take? How long is this going to take? And from that, I just sum it up. I get, okay, sequence 1, here's my estimate. I do the same for sequence 2. So that's what's written here. For each sequence, look at each operation, estimate the cost. This gives you a cost for the whole sequence. And now you just pick the sequence with the lowest cost. That's query planning. Now, how do we know how much an operation costs? So let's look at this again. Okay, here, and we will see cost estimates, very simple ones in the following. Yeah, I kind of can say how long it will take to compute the product of these two tables, because I know the tables. I can just look, oh, this one has 1,000,000 rows, this one has 1,000 rows, so it's going to be 1 billion rows in the result, and this is that's how much it's going to cost me. Here, or here, let's take this operation, that's already harder, because this takes as input something from another operation. And how expensive is this depends on how big this table is. So to be able to estimate the cost of this operation, I need an estimate of the size of my input table. So cost estimates for query planning, and this is a whole, people are working on this their whole life and nothing else, because it's important. But what I just explained to you, if you want good cost estimates, you also need estimates of the size of the input tables. And we will see example for this now as well. So if you want, how expensive is this project operation? And project, remember, is a very simple one. It's just taking the second column from a table. But still you have to copy something. It's basically, how big is this table? So to have a cost estimate for this one, I need a size estimate for that one. And that's why cost estimate is really, you need an estimate for the cost and the size of each operation. What it says here. Estimate for the size. And and in real query planning, you can even gather much more statistics. Not just the size, maybe also the distribution of the data in a table, because that might be important. And You could do a whole lecture about query planning. As I said, it's their specialty in research, but let's do something very simple just so that you see how it's done in principle. Here are some simple estimates. Project just selects columns from a table. I have a table, here I have column indices, distinct or not. How much, let's say this input table has n rows, k columns, and k prime is the columns in my result. So I'm claiming this is the size of the result, right? You don't delete any rows, you have n rows, you have k prime columns in the result, you have to produce that result. To go to my table T and copy these values to the result. So that's essentially the cost. That's a pretty good estimate here. If you do the distinct, so I swept that under the rug here, you have to do additional work, you have to maybe sort it or compute a hash map. I just ignored it. It's an estimate. I just want an idea how expensive is this going to be. The number of rows, I can actually say it exactly. It's the same as in the input table. And the number of columns, I can also say it. It's an argument to the project operation, how many columns. Here are some assumptions, and let me just, why doesn't the animation work here? Let me just, I think we fix that on the fly. That's interesting. So that looks obvious, like for the simple, but even that is not simple. So I'm just giving you hints here at why that is actually a big research area and not so. So why is that a good cost estimate? I'm saying, yeah, you have to produce the result table, so you have to copy every element there. Yeah, this is true. If you have to really iterate over every row from your input table. You iterate over every row and then you say, okay, let me just pick these column values, copy it to the result. And this is actually what you have to do now it depends on how your table is stored. Do you store it row by row order, it's how it's called? Then this is a reasonable estimate. But actually, you could also store the tables column by column. Didn't even talk about that yet. How do you store a table in your machine? Could just store it column by column. And now if you have project, you're basically just saying, okay, pick these 3 columns. You don't maybe don't even have to copy them. You could just say, okay, these 3 columns, they are already here. I just store a pointer to them. And then this suddenly becomes a constant time operation. We're not going into any details here, but you see that it depends on details of the implementation, of the representation, obviously how expensive operations are. And then depending on that, you might get totally different query plans, like these trees, how you execute a query. But that's just, these things I just mentioned, we don't go into any depth in this lecture because this is a database introductory course. Now for select, so that selects row according to this function, which says, is this row, should it be in there or not? Okay, let's look at, and again here, the animation, let me fix it, so that So I'm saying, okay, the result table is as big as the input table, so the cost is n times k. And now, how big is my result? Well, that depends. Here I make some arbitrary assumptions. I'm saying, okay, I'm iterating over each row of t, and now I have to evaluate phi. This here can be a very complicated function, right? So now I need an estimate of how expensive is it to evaluate for each row. What we have seen so far is always, is this equal to this, but it can be a super complicated function, depending. And how do we know how complicated it is before executing it? It might be very expensive on some rows, very cheap on other rows. And then the question is, on how many rows is it true? If it's always false, I just have to evaluate it, not copy anything. So a lot of unknowns here. And that's typical for query planning. To estimate the cost, you have to know a lot which you don't know. So here I'm just assuming It's cheap to evaluate, and it's true half of the time. Totally arbitrary, but actually better than nothing. At least I have something now to compare different operation sequences. Here just some things you could do. You could just evaluate the function on a number of rows. Let me get a feeling for this function. I have a table with 1,000,000 rows. Let me evaluate on 1,000 of them to get a feeling. Yeah, that's the average cost. It's true 1/10 of the time, or something like that. And also, it's more complicated. Maybe your predicate is of the kind greater or equal to 8.0, and maybe your table is sorted by that row. Then you don't even have to go over the table. You just do a binary search and see, okay, this is sorted. Let me just find the row with the first one where it's 8.0 and take everything above then. And then the cost estimates completely change. So again, what's here in the reality check section is just to tell you how it's really done. We are not going into any depth here. Okay, we'll have a break in a second. Let me just make some things blue here, because we can't continue before things which should be blue are blue. Okay, the estimates for that's actually easy because it's always expensive. So, but writing it down, it's also non-trivial. I mean, what's the size of the result? The result has this many rows, number of rows of one table times number of rows of the other table, and the number of columns adds up, right? So this looks strange, but if you think about it, that's just the size of the result table. And you have to produce the result table, and that's just the cost of it. And actually we know, here we could write equality, and let's just do that. We know how big the result is. So the cost estimate for the Cartesian product is actually pretty simple, because it's always expensive, and I've written that there. Let me just... yeah, these are pretty accurate because there's not much... I mean, let's say you're given the task of implementing Cartesian product. I mean, what do? You have to compute it. You have to do 2 nested loops and compute all combinations. There's not much you can do. You can't make it more. If you have a large output and most of the work is produced, the output, that's why good query plans, any query engine will try to avoid Cartesian products as much as it can, which is the reason for the last part of the lecture, which we will see in a few minutes. And I think now we make a break and we resume in 5 minutes. Thank you. Let's go on. So, query planning. And now let's maybe... So we could now... So this is something we have seen earlier. We have 2 sequences, and now we have to figure out which one we should take. And now we have some cost estimates. Maybe let's not do it for all 3. You can do that as an exercise. It's also part of the exercise sheet. But so I'm assuming everything is all right, right? You can hear me again and so on. Let's do the cost estimates here. So let's say this has these sizes n1, so this is number of rows, and this is number of columns. I always use nm for rows, k and so for columns. And this here has these dimensions, k2, and this here has these dimensions. So I claim that the cost of this final operation is the same for both. I mean, the cost for a Cartesian product, that's what we say, it's the size of the final table, which means it's n1 times n2 times n3 times, and then it's this sum of the, I mean, it looks, it's actually quite simple, right? It's just a bit tedious to write. It's the same for both. In whichever order you evaluated the cross product, in the end, you have this huge table with all combinations of all rows from the 3 tables. So the second, and that's what some of you said, after a while, that that they're actually the same. Now let's look at this one. So this is cost. Yeah, what's this? Movie and persons. So that's n1 times n3 times k1 plus k3. And here the cost here of the first operation is, it's movies and cars. So it's n1 times n2 times k1 plus k2. So it's actually, it's pretty simple, right? There's nothing, it's just these strange expressions, you write them down. And now let's, maybe we said that it's about real data. So if we have real data, which of these tables is the largest, would you say? Which one has the most rows? So let's compare these two movies compared to cast. Which one has more rows? Yes? Yeah, cast should have, right? Every movie will probably have one actor, but will have many actors. So we expect N2 to be much larger than N1. Let's just write that down. So this is N1 is probably. And what about? Now it depends a bit on N2 and N3, who we have in our, whether we have all persons, but let's just assume we have only, so it's and this is under the assumptions. If we only have actors, then that's certainly true. Actors in persons. But this is something, I mean, if the tables are given, we could just compute it, right? And then it's clear. Then the difference in the costs between these two is the difference just in the first operation, and then this is more expensive. And this is also what some of you said, right? Here I have the bigger table. So if the end result is the same, that's actually a pretty general principle. I do something in a certain order, the end result is the same, no matter in which order I do it. Start with the smaller ones first, right? This here is starting with the bigger ones, N1, N2. So according to the above, we have N1 times N3 is smaller than N1 times N2, so we prefer sequence 1. Now we could do the same, and I leave that as an exercise. The intuitive thing, you can now make it, you could do the same thing now here, right? You could just write the costs here, and please do it as an exercise. You should absolutely do it. I think it's even more instructive if you do it yourself. Here the end result will again be the same. But the cost of this will be, and here you need, of course, maybe we do it for, let's do it for that one as well, and leave the third one open. So here we have, let's also make, just so that you see it for one more example. So what's the cost here? cost here is N1 times N2, and please pay attention that I don't make any mistakes. K2, and also we estimate the, and this is selecting row, so the size, our size estimate here is, we know the size of this one, it's just the same, it's N1 times N2, so this is the number of rows, times K1 plus K2. We can estimate the size pretty exactly, and then we have a cost estimate for this one here. And what did we say? We had this very simple cost estimate. Let's just go with that one, where we say the expression is simple to evaluate, and the cost is half. I think the cost was just going over the whole table, right? That was the cost. N1, N2. We don't need the... I think that's what we said. For the select one, the cost is essentially going over the whole table, because you have to go over each row and evaluate each of them. Okay, let's do the same thing here. What's the cost estimate of this one? Movies, what's the cost estimate? What did we say? We say we have to go over the table, right? And evaluate. So here the cost is N1, K1, and the size estimate is, what's the number of rows? We said we filter out every second row, so it's N1 times K1 divided by 2, and it's the same number of columns. So that remains, no, it's not N1 K1, it's N1 over 2. That's what we said. N1 over 2 times K1. So what's the cost estimate for that one? Now we take the cost estimate for, so T1, we know it's, now it's N2 times N1 over 2 times K1 plus K2. So we take the cost estimate we had for T1, the size estimate. The size estimate is that this filters out half of the rows, and so that's N1 over 2 here. That was our assumption. And now if we look, I mean, now this one is obviously better, right? Because here I have the same huge cost twice. I have this N1 times N2 twice here, and here I only have it once, and here even with only half of the cost, and this one is relatively cheap. And here's one important message, and you should also do that for the exercise sheet. And the important message is, and let me say this because it's really important, there are even papers about this, these estimates, I mean, here we use this super crappy estimates, like we don't know nothing about our evaluation function, we just say it will reduce it somewhat by a factor of 2. It doesn't matter. It's still enough to determine that this query plan is better than this one, right? Even with a very cost estimate, with a very simple estimate, with a very simplistic estimate, it was enough. Actually, any estimate, because this plan just avoids doing going over this table twice. So that's really important. So yes, please. Thank you. Yeah, this is the same error from before, right? Let's now keep the... Thank you very much. Let's fix that. Yeah, I did a lot of iterations on these slides. Actually not so easy to explain this stuff. Okay. And this one I leave open. This one, that was this interesting one where you can leave out the Cartesian product altogether. It's clear what will come out, right? Here you have the cost of this one, which is huge. Here you don't have it. Okay. Oh yeah. Let me show that one. That's interesting. Actually, I can ask. Did I want to do it at that point? Yeah, let's do that. Let's go back here. And maybe now is the time to explain something about the exercise sheet. So for the exercise sheet, now we just copy, because Daphne, and it's a problem with the authentication of the Uni accounts. It doesn't work at the moment for anybody. So first thing, for the exercise sheet, you now get much bigger data. So in the last lecture we played with toy data. Now you get bigger data. You got a lot of TSV files. They are somehow related to the last sheet, but more information and bigger data. I've copied the table here. So for example, now I have a movies TSV, which is much bigger. Yeah, so over 100,000 movies, so it's a table here. Now we also have, let's look at the roles table. This now has 3 columns. It also has the role. Not everybody, somehow the role is missing. So here we have someone with this ID playing in a movie with this ID, the role of Ophelia, and so on. So these tables are pretty big now. This is now over 1 million rows. It's still small compared to the real world, but for our purposes now it's a really big one. And we have all kinds of other tables here. And let me do the following now. Let me just load them into SQLite now as follows. So here I'm just creating the corresponding tables. I hope that's correct, and then I'm importing the data. And let me do the following. So we already did that in the last lecture, so that I can say something. SQLite. No, I want it to be stored in a database file so that I can reuse it. Now this is just creating the tables and importing the data. You can see it takes some time, but shouldn't take too long. At least it works. That's good. And while it's doing that, let's maybe write a query. That was wrong, SQL. Which query should we take? It doesn't really... I don't know. Select, and let's also maybe take timer on. Select, I don't know, movies. Let's see, let's take from. We have movies, we have persons, we have roles. Where movies. Now I'm not sure what the... Let's just look at the schema. Let's maybe... And I should maybe make this smaller now. No, let's make it larger. NVIM. Let's... So movies, it's called movie ID now in my schema. Again, movie ID is role move. Oh, thank you. It should be, yeah, it should be roles. If I make the mistake here, and it will, okay. And roles, yes, thank you. Nice one. Okay, so let's just go with that query. And yes. Sorry, too many things going on at the same time. Thank you for correcting me. So I have this query, and now let's query SQL, and now I can just pipe it. I already have my tables in here. Let's see what it does. SQLite 3. Okay, that's too many movies. Let's maybe, I could do the following. I could just count. We didn't have count yet, but that's just counting the number. Now I probably crashed this machine. Okay, see, already producing the, okay. So this is a very simple, timer on. You just get timing information. You get the number of rows in the result. And now let me do the following. Let me do the query twice and write just before the first one, explain query plan. That's what on the slide. See, now I get this, now I see what it does. Scan, roll, search. So it's kind of telling me what it does. It's using different operation names than the ones we're doing. And we'll come back to that at the end. I just wanted to show it for now. That's how you can do it. You just have the query and you write explain query plan before the query. You can also do just explain. That's also written on the slide. It's interesting. And now I get a really low-level query plan. So this is something which SQLite provides. This is basically on the instruction level what it does. Rewind, I think, is something. This is like nested loops here, and now it does all kinds. These are registers. So we will not go into that, but I wanted to mention that this exists, and you can do it to get an idea of what the query engine does. It's actually very important if you use these things in practice to see what's going on. Unlike much of SQL, this is not standardized, right? This is now what you just saw is what SQLite gives us. Other database engines will also do something like this, but they might do it differently. And let's just very quickly go to what I showed you here. So here, by the way, this is our explain. This is our own engine here. Just so that you see that you also have all the components here. So for example, here you have our size estimates. Here you have the operations. Here you have estimates for the cost of the query, estimates for the size of the query, and so on. So that's our, and behind this is a text format, which is just displayed as a tree here. Here it's also kind of a tree, right? Shown by this ASCII. And we will come back to this in a second, but you might want to play around with it in the exercise sheet. So the last part, joins. That's also important for the sheet. And maybe let me first explain a little bit, and then I can now show you the sheet. I will show it to you. So the following is very frequent in a SQL query. We have seen this a lot. You have two tables in the from clause. You're kind of combining them, and then you have something like one column from this table is equal to one column from that table. We have seen that a lot. And it comes, you did that for the last exercise, if you design your tables in a certain way, like spreading, how we did it. Here I just have the movies, here I have the persons, here I have the roles with IDs. It's natural that you have such queries. And in this query we had it twice, right? Here I hope this is correct now. I have movies and persons. And then I have it twice here. I have this pattern twice. And now it turns out that it's a good idea to define an operation specifically for this combination. So we don't want to do, and I've said this many times, first compute the cross product, the Cartesian product of three tables, and then do these select operations. Select, they are called, right? When you filter out rows. But I want an operation specifically for this. And this operation is called the single column equijoin. And I have a slide explaining why it's called like this. And here's how it's defined. So understand, so far I've just defined 3 operations, but I can define more operations. And I just tell my database engine, look, there's also that operation. If you think this is useful, use it, and then you can generate all kinds of query plans, sequences of operations, and try to figure out which one is the best. So even if these 3 operations which we have seen are enough to cover everything, it makes sense to throw more operations into the mix, because maybe I can be more efficient then. So this is not needed for correctness or coverage, it's needed for efficiency. And it's called a join. It takes 2 tables as argument and 2 column indices. And what it does is pretty simple. You have seen this a lot now. So this first column index is just a column index from the first table. This is from the second table. And then the result is, like in the cross product, you concatenate the columns. So that's like in the cross product. But the result is you just get those combinations for which the values in these 2 columns are equal. And you can already see here why it's called the equi-join, because you have equality here, single column, because it's just 1 column for each. I have a slide on this. This is kind of doing 2 things in one. Combining the tables like in the cross product, but then only combining those rows for which this condition holds. It's doing 2 things at once in one operation, and this operation has a name, and it's like the most important operation in databases, which is why it has its own symbol here like this. It's a join symbol, but it's just the same as this one. And here's an example. Okay, something went wrong here with the formatting. And this we are going to, I will keep it now, I will fix it later. It wasn't so easy to find an example which works for all the following slides. I hope this is correct now. So here I have 2 tables now. One is called Profs, one is called Studis. This one has IDs for courses, so these are IDs from HISIT 1. Abbreviated IDs, and I have the name of some professors here. So here this is, I think, artificial intelligence course from some semester, used to be taught by Frank Hutter and Wolfram Burgert, who's no longer there, but doesn't matter for now. This is our course here, this is another course here. And here I have some student IDs, made up of IDs of course, and the courses where they participate. And here I have the result of this join operation. Let's maybe not look at this. If it's not correct, please tell me. This is how I would write it in SQL. Combine these 2 tables. There shouldn't be a semicolon here, of course. That's part of the same query. And now that I don't know why this is so. The indentation got lost here. So now we fix that. And let's just check that this is correct. So now I get all combinations of rows of these 2 tables, but course, the value in course has to be the same. And please check that it's correct. Maybe I made a mistake. And the size of this is now not so easy to predict, right? It really depends on the tables. It could be empty, it could be the whole Cartesian product. Think about it. It can be anything in between. So this says join these 2 tables just in the way how you would do it for the Cartesian product. And there's again, you see, PowerPoint capitalizes even though I don't want to. So that's why. And it will now only take those combination of rows where the value in the course column is the same. And this is the 2. It's just take this as join column for the first table, take this as join column for the first table. Consider all combinations of rows where this value is the same. So for example, we have here Brox V720. We don't have this here, so we have no such row here in the result, right? This makes sense. We have Bast V1304 and we have this 1304, so we would expect one result with this combination. Yes. And now we have this V2040. We have it 3 times here, and 2 times here, so we would expect 6 rows in the result, and we do have 6 rows in the result. So that's important to understand and look at this at home. That happens with understand that the join operation is in principle like the Cartesian product. It's just filtering out the stuff where it doesn't match, but on a lower level you also have this Cartesian product thing going on, right? Now we have all combinations, and let's maybe highlight them here. So for example, here, this matches. These rows all match, and so I get all 6 combinations of them. This is very typical for databases, and this is also why the equijoin can be pretty expensive. If you have a lot of equal values there, yeah, and it will correspond to these 6 results here. Is there any question about this, what the equijoin does? Yes, please. Oh, an error. That's... Yes. Yes, you are completely right. There's an error. Thank you.
There's also a small typo in the where for start cookies without the...
That was PowerPoint correcting me. Thank you very much. Let's check if there are more errors. And what you should get in the result is, by definition of the join, these columns should be identical. You should have the same column twice. Now it's debatable, and we debated this, whether you even want it in the result. You could define the operation such that you only have this column once. But in the literature and also in many engines, it's actually done like this. And I think it's nice because then you see how it's related to the Cartesian product. It's like the Cartesian product with fewer rows sometimes. And understand, let's maybe stick with this table a little more. Understand the 2, I think it's on the next slide, but let me just say it here. 2 extreme cases here. If these 2 are disjoint, no intersection, then the result is empty. If all the values here are equal, there's just one value here, and it's the same value here, then I get the full Cartesian product. So I can get anything between empty table and the full Cartesian product. So it's not that the equijoin is always cheap. It typically is, because typically here, if you think about real data, you will have many different values, also some equal values. Here you only have equal values when you have several lecturers for the same course. Here you have equal values if you have several students for the same course, which will happen. It's also not easy to predict the size of the result. Okay, let's go on. So why the name? I think that became clear now. It's called single column. You could also have 2 columns for each table and say the values have to be the same in both columns. Then it would be a multi-column join. And this thing exists, but we don't deal with it here. And it's equijoin because we have this equality here. So that's on this slide. And that's what I just said. Yeah, and let's just the obvious thing. So let's, this is our query here. And now we have a new, that's what I said, we have a new operation in the mix. What's the consequence? Well, we could do it like before. That's how we did it all the time. And this should be, I hope it's not too annoying, these small little mistakes. But yeah, that's just... Oh, and again, Studis was corrected by PowerPoint. So that's my one sequence. I just take the query literal. I'd say, okay, 2 tables. Let's compute the Cartesian product. Then let's select the rows where this is true. Let's just check that this is 2 and this is 4. Here we have another Studis course. That was PowerPoint. I know it. And this is the second sequence. I just say, okay, this is one join. I have an operation for this, right? I have one operation which does the whole query. And similarly, the other query where I have where I have 3 tables and 2 where conditions, that would be 2 joins. One way to do it would be 2 Cartesian products and then 1 select, but I could just also do 2 joins. And now which one is better? I think it's clear. Depending on the implementation, which we'll talk about next, this one is better. Any questions about this? Okay. So now, and this is, okay, is this better? That's the question. I mean, now we have made one operation out of it, but I mean, now it depends on how you implement it, right? I could implement this operation by computing the Cartesian product and then going over the rows. Then I haven't won anything. So this, the advantage of this is about the implementation, and we will talk about this now. And there are 2 ways to implement joins in principle: hash join and merge join. And now you will see a connection in a second to the information retrieval stuff. So the hash join, that's the simplest one, and you will do that for the exercise sheet. And I don't think this is the formal definition, but I think we should do it by example, and then maybe go back to the formal definition, or maybe not. Let's do that. This is, I think, the best way to understand this is by doing an example. So this is the hash join. And this is, I think, we have 2 tables, X and Y. And now it's, of course, we have to decide which one is X, which one is Y. This is symmetric, so we could do it either way, and it's an interesting question, which is the best way. But for now, let me just do it. So this one is Y, and this one is X, and that's my result table. So the first thing I do, what's on the previous slide, it's called a hash join, so I build a hash map for the table X. And I will just look at all the distinct values in the course column. So I will have V720, and this is, and now I remember row IDs here. So these, I now give these in any order. That's important. It's not important what the order is. I just take them in any order. And now I just say, okay, this here occurs in row 1. Then I have this one here. And this occurs in rows 2 and 4. And then I have this other course. And note, I can hash anything I want. So here I'm caching strings. And this is just, what? 304 is 3, yes. So here it's not a very interesting hash map, at least I have some duplicate here. It's 2, 4, so that's what I compute. And let's just go back in the formula, that's the first steps here. These are the rows of X in any order, so it's not important what the order is, I just go over them in some order for now, because I will, so that I can speak of column indices. This is just a set of distinct values. I may have duplicates, so in my example, this set has 3 elements, 3 different courses of the values in the join column. And I need to make something blue here. Now compute a hash map, where I just remember for each distinct value in my join column, the sets of indices of row which contain it. It's actually harder to write it than to do it, right? So that's this here. Yeah, it's simple enough. Now I go over, now iterate over Y. And you have to implement this. It's a good intercept. Now I iterate over Y, and now I just actually don't need the Now I just in any order, and let's start with 1304. 1304, I look it up in my hash table. Yes, 1304 is there, and it's there with row 3. And now what I do, I will just, and sorry, the things here are again capitalized because PowerPoint is doing these intelligent things. And use the opportunity to think about it. It's not even trivial to correct it because it will always counter-correct. But if you correct it enough, you win. It somehow remembers that when you correct it many times, it gives up. That's nice. And I will actually now do it in a different order than on the slide. So on the where I showed you the result. So 1304, I look it up here, it's 3, and I say, okay, now for everything in this set here, I write a line to the result. So let's do that here. I will do that. So I will do 7, 3, 8, 3, 4, 3, 6, V, 1, 3, 0, 4. And here it says 1304. I think I should, it says 3, so I should take row 3. It's actually simple if you understood it, but you have to understand it. V1304. And now let's go on. Now I take the second one. I say, okay, V0240, is it here? Yes, it's there with 2 and 4. And now I take all combinations of this row with rows. Yeah, I do it with row 2 and I do it with row 4. So let's just do it. So I will have this twice now. 3, 4, 8, 7, 4, 6, 4, V. And that's also pretty much how a database engine will implement it, how you will implement it for the exercise sheet. V2040. And now I will take row 2 here, which is this one, and I will take row 4 here, which is this one. And so on. I don't fill up the whole. You get the idea, right? Now I go here. This again, I look it up. I get 2, 4. So I take all combinations of this row with row 2 and 4 from my table X. This one does not exist. So nothing happens. This one again. So this is how I fill up 4 more rows. This one does not exist, and so on. And let's go quickly jump to the formal description. Yeah. So you go through those rows in any order. Let's maybe see that in the here so that I can correct the colors. Here's also some blue. Yeah, it's just the informal, it's just a formal description of what I just said. It's actually easy, it's just hard to describe it formally. Any questions about this algorithm? How it works? That's what you're supposed to implement. Maybe now is the time to show you the exercise sheet, because we are almost done. And I think I will also not say much more. The exercise sheet is really interesting. We spent a lot of time on this, also on the lecture, but also on this. Let's see, I should have. So the first exercise sheet will be to implement a very, very simple database engine where you just implement 3 operations: project, select, and these are really very simple, selecting a column, selecting rows, and doing this join, and you will implement the hash join. That's the first exercise. And you just have so here is and don't be afraid of the files we're giving to you. They are pretty big. So here it's like a function, and you will recognize this. It's the function. It has basically the same signature as what I defined on the slides. And here you have extensive doc tests. And we are giving all the code for reading in the tables to you and also for pretty printing the tables. And this is not something you have to do. So here it just says, okay, if for a certain input table here, which we also give to you, you call this operation, then you should get this table as a result, and so on. And then you should just implement it here. And it's very little code, but you have to understand what you're doing. You should also implement select, and you should implement join. So that's exercise 1. You should just implement these operations. And we also, is there anything for the student to do in table.py, or is this just given? Nothing to do? Yeah, we just give it to you. So Sebastian did this. So it's all the annoying work of reading the table and so on, and pretty printing a table. And it's actually nice that you can do this. So after this exercise, you have written a very small database engine yourself. And what's the other one? Oh yeah. Okay, and then the second exercise is, and now pay attention, or maybe I show it to you in the result. Yeah. We are giving you a SQL query, only one SQL query, a pretty complex one, but it's a typical SQL query which you have. You have more data, you have it in different tables. Here it's movies, awards, and so on. And here it's like we want everybody who played in a movie which won a Golden Globe and has a certain higher score. So it has a lot of joins here. By the way, let me briefly mention it. This cars this because in our Python program we don't have, for simplicity, we don't have integer reals, everything is text. That's the only reason why you have this artifact here in SQL. Does it still work, Frank? What?
I'm not sure.
You are not sure?
I'm not sure. There's a message I didn't know.
There's a message. Oh, today is one of those, everything, let's...
I won't touch it.
What does the message say? Merry Christmas, or? R0, that's certainly a database error code. Okay, R00. I mean, the camera works here. Okay, the combination of things that went wrong today is pretty amazing. I don't see the relation between Uni account LDAP problems and this one, but I'm sure there is a relation. So this here is just an artifact of, in our Python program, everything is just text. And so if we want to compare something like an integer, we need this cast. But you don't have to worry about this in your program. What you should do, you should translate this manually into a sequence of operations. This is something a database engine does automatically, of course, but that would be a whole different game, automatically translating a SQL query to a sequence of operations. We have seen this many times. You do this manually here. You just write, like we did it, a sequence of operations. You implement these operations and now you call them. And you do this 3 times. You think about 3 different sequences of operations, you implement them, and then you run them. Of course, the result should be the same each time. And then you also run a SQLite query. You can just put this into SQLite and see if the result is the same. And you compare the running time. I think it's a great exercise to understand what we did today, to understand all kinds of details also. And you should absolutely do it, of course. Okay, and I think this, yeah, let's do the running time and then we should finish. No, I don't think it's important now to do the running time. Let me just mention, and we will do that in the next lecture because you don't need it for the sheet. There's also a merge join. And I will just do this in the next lecture. There's also we can do the exact same thing differently by sorting these columns, and we will just continue with that in the next lecture. But you don't need it for the sheet. For the sheet, you implement a hash join. So let's see. There's a question in a Zoom flashed Karte ist voll. pretty briefly a minute ago. Karte ist voll.
Beschaffen dürfte nicht.
Ah. Should not be full. Karte ist voll. You get the best sequence of commands for a query. One has to calculate the cost for every possible sequence. Should we know how to construct? Okay, that's a good question. The question is for the exercise sheet, as I just explained to you. The number, that's a different problem. We are not considering generating all possible sequences for a SQL query. It's a very hard problem. You can do this with dynamic programming, only generating the optimal one. It's not part of your task. Just generate 3 different sequences which come to your mind. And then estimate their cost and try to find one where you think this is a good one. Also pick ones which are bad. It's up to you. But you don't have to, it's too much work. Just think about 3 different ones and one which is hopefully good. Any questions about this for now? Okay, so do the exercise sheet. It's very valuable to understand what we are doing today, what we did today, and we will continue in the next lecture. So thank you, bye.